Hello. In this video, we are going to discuss the Chatelier Principle, and perhaps more importantly, we are going to illustrate it using specific, concrete numerical examples. First, we will discuss a generic reaction where we have A and B reacting to form C and D, and the specific stoichiometric coefficients are shown in red, where we have A moles of the substance A, B moles of the substance B are the reactants, and then our products are C moles of the substance C and D moles of the substance D. So a reminder that the stoichiometric coefficients are the lowercase red letters. The actual substances involved as reactants or products are denoted by the capital large blue letters. At any time during our reaction, we can define this quantity Q, the reaction quotient, which is an expression where we have the current concentration of C to its stoichiometric coefficient, the concentration of D currently, and it to the power of its stoichiometric coefficient, divided by the products, their concentrations, to the power of their individual stoichiometric coefficients. The important thing to recall about the reaction quotient Q is that we can define this quantity at any particular time during the reaction. So for any particular reaction, we have a very large number of possibilities for Q, even if we're staying at one specific temperature, which will be the case that we're going to impose in the discussion in this video. Now, when we reach equilibrium, this quantity Q, the reaction quotient, will be equal to a very important quantity K, which is the equilibrium constant. This quantity depends upon the reaction and upon the particular temperature. If we change the temperature, the equilibrium constant will change. Now this relationship between Q, the reaction quotient, and K, the equilibrium constant, at equilibrium is both an if and only if situation. So if we're at equilibrium, we know that Q is going to be equal to K. On the other hand, if we already know ahead of time what the equilibrium constant is, and we find that Q under some set of conditions is exactly equal to K, then we know that we are at equilibrium. Suppose we find during our reaction that Q is less than K. We can make a great amount of interpretation by using the fact that Q has the form of a fraction. If Q is less than K, that tells us that relative to the equilibrium value, that the product of the concentration of C to the C power times D to the D power, this expression involving the products, is smaller than it would be at equilibrium. So we don't have as much products as we would at equilibrium. On the other hand, it tells us that the denominator, which involves the concentrations of the reactants, is larger than it would be at equilibrium. So we have too much reactants and not enough products. As a result, relative to the equilibrium case, we are too far to the left in the reaction. And since we are too far to the left, the system will respond to being out of equilibrium by shifting to the right. In the process of shifting to the right, it decreases the denominator expression and increases the numerator. And as a result, it makes Q larger. Now suppose that our computed value of Q, the reaction quotient, is larger than the equilibrium constant. that tells us that the numerator expression here, which involves the products, is too large. On the other hand, the expression for the denominator of the fraction, which involves the reactants, must be too small. So that tells us, relative to equilibrium, we are too far to the right in our reaction. And therefore, the system, to respond to this stress, is going to move left. The final possibility is that Q is precisely equal to K. If we find this to be true, we know from our condition here that we are actually at equilibrium. And the system will appear to not move. Remember that equilibrium is dynamic, so even when the relative concentrations are not changing, we are still having a dynamic equilibrium. So that means that the reaction going from left to right is precisely balanced by the rate that the reaction goes from right to left. We can use Q, as we see, to predict how the system is going to move towards a new equilibrium. So one thing we can keep in mind is that systems like to be at equilibrium. If we put a stress on the system that moves it away from equilibrium, the system will then move at some rate towards equilibrium. What it will not tell us is how quickly we will move towards equilibrium and how long it will take for us to achieve equilibrium. But it will tell us in which direction the system will move. For the remainder of the video, we are going to concentrate on a specific reaction. In this case, this is the so-called Haber process, where 1 mole of nitrogen gas reacts with 3 moles of hydrogen to form 2 moles of ammonia. For this specific case, we are going to see how various stresses to the system are accommodated by the system, and how we can illustrate Le Chatelier's principle for this specific reaction. So for this reaction, we can write out explicitly our expression for the reaction quotient Q. Notice that we have a reaction and it involves gas molecules. So we could consider our equilibrium constants and our reaction quotients either in terms of partial pressures or in terms of concentrations. For the ease of application, for this video, I'm going to do it entirely in terms of concentrations. If you were to do it in terms of partial pressures, the ideas work exactly analogously. So we have the concentration of ammonia to the second power divided by the concentration of nitrogen times the concentration of hydrogen gas to the third power. Let us also make an assumption here to make the example as easy as possible to apply. Let's assume that we're doing this reaction at some particular temperature where the equilibrium constant happens to be exactly 1. And this is an arbitrary value. We're just picking 1 for this example just to make it easy to see where we are, because we will be computing various values of Q and we'll be able to recognize whether or not we're at equilibrium simply by comparing it to K. And since K is an easy number to recognize, the number 1, that will make that easier for this particular video. To make it easier to see what we're doing when we make these various different changes in the system, let's just pick one arbitrary state. And this arbitrary state that we're going to use as a reference, as a comparison, is the state where the concentration of nitrogen is equal to the concentration of hydrogen, which is equal to the concentration of ammonia, and they're all set equal to 1. We're just doing this simply for convenience, and then we realize that if we substitute these values into Q, Q is going to be equal to 1. Since Q is equal to 1 and K is equal to 1, it tells us that Q is equal to K. Therefore, this reference state is a state where we are at equilibrium. we can have many, many possible states where the equilibrium constant is equal to 1. So we have various different ways of achieving equilibrium. The simplest way we can do it for mathematical purposes here is just to take the state where each of the gases has a concentration of 1. So for our first example, we're going to take our system as it is here at equilibrium, and we're going to keep the hydrogen and the ammonia with exactly the same concentration. But we're going to increase the concentration of nitrogen from 1 to 1.2. So we're increasing the concentration of one of the reactants, and we're going to see how the system responds. Well, first, let's see if we're at equilibrium to begin with. We're going to compute the value of Q. And if we do, under these particular conditions, the value of Q is going to be equal to 0.833. So what do we notice about Q? Well, we know that K is equal to 1, so therefore Q is less than K here. As we had seen previously, if we have a system where Q is less than K, the system is not at equilibrium, and the system is too far to the left, it has too much in the way of reactants, not enough products, so therefore the system will shift to the right, thereby decreasing the amount of reactants and increasing the amount of products. And that way, the fraction Q gets larger and eventually will approach and equal the equilibrium constant, which in our case we can recognize because we've set it to be equal to 1. So we know by the Chatelier Principle, the system is not at equilibrium, the system will move to the right. So in the process, eventually we will reach equilibrium. When we get to equilibrium, Q will be equal to K, and at that particular point, we have these values. So the concentration of nitrogen will have dropped from 1.2 to 1.17. So that's one of the things we imagine as it shifts from left to right. The concentration of N2 will decrease. Similarly, the concentration of hydrogen will have dropped from 1 to 0.96. So it dropped. On the other hand, the concentration of ammonia, which is our product, has gone from 1 to 1.03. If we compute the value of Q now, we will notice that Q is equal to K, so therefore we are now at equilibrium. And we achieve this after having swamped the reaction by having increased the concentration of one of the reactants. A second way that we can stress our system and move it away from equilibrium is to remove one of the products. In this case, our product, ammonia. So we're going to remove some ammonia, we're going to lower its concentration, and see how the system reacts. So specifically, let's leave the concentrations of nitrogen and hydrogen equal to 1, but let's reduce the concentration of ammonia from 1 to 0.8. We can compute the value of Q in this case, and we see that Q is equal to 0.64. Since we know that our equilibrium constant at this temperature is equal to 1, we realize that Q is less than K. Because the system is in a situation where Q is less than K, we are too far to the left, and the system has to respond by moving to the right. In the process, it will consume some nitrogen and hydrogen, and in the process, create more ammonia. And that way, Q will approach K. After moving to the right, equilibrium will be reestablished. So when we reestablish equilibrium, the concentration of nitrogen will be 0.97. So it will have dropped from 1 to 0.97. The concentration of H2 will have dropped from 1 to now 0.91. The concentration of ammonia will have increased from 0.8 to 0.86. At this point, even though we don't have room to write it in, Q is going to be exactly equal to 1, so we know that we are at equilibrium. A useful thing to notice is that we have one set of conditions here where everything is equal to 1 and we're at equilibrium. And down here we have another set of circumstances that have different concentrations but yet is still at equilibrium. The third type of stress on our system at equilibrium that we are going to investigate is external pressure. This might be achieved by pushing our reaction vessel in such a way as depressing a piston so that the volume gets smaller, and then the pressure of the reactants will increase. Notice in this particular reaction that for the reactants we have 1 plus 3, 4 moles of gas, while as product we only have 2 moles of gas. We predict that in any system where the number of moles of gas decreases, that it will react to external pressure by shifting to the right. By making fewer moles of gas, we decrease the pressure. So let's look at that specific example. Let us assume that we've supplied sufficient external pressure that we've reduced the reaction volumes exactly in half. Since we have the same number of moles of gas, but now in 1/2 of the space, we've doubled the concentration. So this is equivalent to taking a situation where the concentrations of each of the gas is equal to 1 and transforming it to now the concentrations are each equal to 2. So notice in this external pressure example that we are able to simultaneously change the concentration of all the reactants and all the products simultaneously. So we want to see how that affects equilibrium. So now we simply substitute 2 for each of the expressions in the reaction quotient Q, and we would find that the reaction quotient now is a value of 0.25. We know that the equilibrium constant is equal to 1, so therefore we have found that Q, again, is less than K. We are too far to the left, and the system will respond by shifting the equilibrium to the right. Since Q is less than K, the system is going to shift to the right until it achieves a new equilibrium. When equilibrium is again established, the concentration of nitrogen gas will be 1.817. So notice that was a drop from the value of 2. The concentration of hydrogen will be 1.45, which we notice is a drop from 2. But the concentration of ammonia is now 2.37. So we see that the system really did move to the right. It decreased the concentrations of the reactants, and it increased the concentration of the product. There's something else here which we can calculate very quickly. Since each of the 3 gases has a concentration of 2, the overall concentration is 6, 2 plus 2 plus 2. So we have a concentration of 6 for the moles of gas. Once we reach equilibrium, we add the values of 1.817 plus 1.45 plus 2.37, and we see that now this is equal to 5.637. So we went from a concentration of 6 to a concentration of 5.637 moles of gas. So that will exert less pressure, so therefore the system has relieved the stress of the additional external pressure. For our final quantitative example, we are going to look at the case of the addition of an inert gas under the condition of constant pressure. This inert gas, for example, might be argon. Since we are under a constant pressure circumstance, the volume of our system can change. So again, we imagine an example where a reaction takes place inside some sort of piston that is free to move. So if we add sufficient inert gas so that the volume doubles, so the piston increases the volume of the reaction chamber so that it's twice what it was before, now we have the same number of moles of gas, each of which is in twice the volume it was before. As a result, the concentrations have dropped from 1 to 0.5 for each of the gases involved. So We were at equilibrium, where everything had a concentration of 1. We've added the inert gas under a constant pressure circumstance. The volume has changed, and to make the math easy, we're taking the situation where we've added sufficient inert gas so that the volume exactly doubles and the concentrations have dropped by 1/2. We now substitute 0.5 or 1/2 for each of the expressions in Q, and we find now that the value of Q is equal to 4. Not only is it not equal to K, so we know that we're not at equilibrium, but now we have the situation where Q is greater than K. So that means that we are too far to the right, and therefore the system, to achieve equilibrium, will shift to the left. Eventually, the system will move left far enough that we will again achieve a new equilibrium. When we get to that point, the concentration of nitrogen now will be 0.552, the concentration of hydrogen will be 0.66, and the concentration of ammonia will be 0.4. So notice that the concentrations of nitrogen and hydrogen are greater than a 0.5, and the concentration of the ammonia went from 0.5 to 0.4, all of which is consistent with a system moving from right to left. I thank you very much for your attention. As always, have a good one.